so first you have to note down the variables. Okay. So in this Navier-Stokes equation, so in this Navier-Stokes equations, variables are like U, V, W, pressure, temperature, okay. Time is also variable, and then X, Y, Z, okay. Independent variable, dependent variables are there. Now, non-dimensionalization means non-dimensionalization of these variables. Okay, so non-dimensional variables, like U star, V star, W star, P star, T star, tau, T will become tau, X star, Y star, G star. Now these are having units. These are unitless. These are having units. These are unitless. Okay. We need a certain scaling parameter for this velocity, which is in meter per second, to convert it into non-dimensional. Okay. So what can be a scaling parameter? So scaling parameter will be a characteristic velocity. Okay. For velocity, it will be a characteristic velocity. For pressure, it will be some characteristic pressure. Characteristic pressure means suppose you are having a flow through channel, for example. Then in this uh, channel flow, you will have either a maximum velocity, U max will be achieved. So we can say that it is a characteristic of the flow. So U max can be used to scale the velocity. Similarly, there can be a pressure, maximum pressure or dynamic pressure or some pressure that can be used as a scaling parameter. Similarly, temperature means temperature difference. So temperature difference between T surface and this T fluid can be used as a scaling parameter. Okay, so maximum temperature difference that can be achieved in this system. Similarly, T, so what is a characteristic time scale? Maximum time scale for which the certain phenomena is occurring. So certain motion is happening in this domain. X, Y, Z can also be these dimensions can also be made non-dimensionalized by dividing them through characteristic dimension. Now for this particular flow, the this channel flow, if you know from the fluid mechanics, that the flow will become fully developed and the velocity profile will look like this. So velocity becomes only function of this y coordinate. Okay, if this is a y coordinate, it becomes a function of y coordinate and it doesn't vary with x. So whatever the things are happening, they are happening in this dimension. Okay. So all the characteristics are happening in this dimension. So characteristic dimension can be taken as h. Okay. So everything should be divided by h. or characteristic dimension. Okay. So we can say that non-dimensional variable, ND variable, will be equals to dimensional variable divided by characteristic dimension. Okay. Like this you can think of. Okay. So for U star already we have said like U inlet velocity, that is U max. For V star is equals to V divided by U in, and W star is equals to W divided by U in. Okay. And X star, in the last class we have shown that X divided by H, Y star Y divided by H, and Z star Z divided by H. T star, T star, we said we need a difference. So T infinity minus Ts. Okay. And that also, the numerator also should be a difference, T minus Ts. Okay. So how we have chosen these variables such a way that U star varies from 0 to 1, V star, W star, X star, Y star, W, G star, T star varies from 0 to 1 or any non-dimensional small number. It can be 1.1, 1.2 also. Okay.
So
And huh,
Ts is the wall temperature of the pipe.
yes.
Okay.
So in this case, TF can be T infinity. Okay. So this T in this case it is TS. Okay, but you will have to see what is my maximum, what is my minimum, like that. Okay. So this difference should be maximum difference. You have to choose this variable such a way that this will be a maximum difference that occur in the system. Okay. And then correspondingly, then T can be a variable, and then you whatever the other variable you have chosen, that you have to put here. So any value T, if you substitute T infinity, then it will become 1. If it reaches that maximum T infinity, if it reaches that minimum Ts, then it will be a 0 value. You understand? So Ts is minimum, T infinity is maximum. T max minus T minimum, that difference will be maximum difference. Delta T max. Okay. P star, P star we have chosen like rho U infinity square. Okay. Now this time, we did not talk about time. So tau is equals to how we can make this T non-dimensionalized. Okay. So that can be done by taking the characteristic velocity divided by the characteristic dimension. Okay. So if you now see, this is meter per second, second, this is meter per second, this is meter, and second get cancelled, tau will become non-dimensionalized, unitless. Okay. So these are the variables. Now these variables we substitute in these equations, in these Navier-Stokes equations. Okay.
Sir,
Yeah.
sir, here
So
we
student,
take a character.
yeah, keep
Here
on,
we
carry on.
take a characteristic dimension as a h in case for a pipe flow.
Huh.
In case of the plate flow, the flow over the flat plate,
Huh.
the characteristic dimension. What will be the characteristic
It will
dimension?
be the length of the plate.
But the velocity and the other things are changed over the y direction only.
But there will be one characteristic, one maximum velocity that will be achieved in the domain. Okay. That is what I'm saying. This characteristic velocity will be a representative of that whole system. So like maximum velocity or the dimension over which the things are changing, you know, that. Or you can have a boundary, boundary layer thickness as your characteristic length. Boundary length will be an appropriate because your velocity is varying with y direction only. Okay, so it is a function of y only. So your boundary layer thickness will be appropriate parameter to scale. Okay. So choosing this parameter is a little bit trial and error. Remember, there is no unique way of defining these non-dimensional uh, variables. Okay. There is no unique method. They can be varied. There is no generalized rule like this also that it should be like this only. Okay. What I'm saying is a bit of a kind of method. So these variables mostly should represent uh, the non-dimensional nature, and they should vary from 0 to certain minimum number. That another criteria they should satisfy. Okay, so anybody can define any other, and then they can get other non-dimensional equations also. Okay, so you have to find a consistent way, and then only you have to go ahead.
So wonder.
Here, the difference of temperature difference divided by temperature difference. No T divided by this. Otherwise, it will not satisfy 0, 1. Yeah. Yes, Karibu.
Sir, can you explain P star and Z?
This is tau.
Oh, that's tau. Oh, okay. Time
Time.
constant.
Yeah. So this is time non-dimensional time.
Okay, sir, and can you also explain P star?
P star
What do you tell me?
is this is dynamic pressure. The bottom bin is a dynamic pressure, right?
Sir, so is that rho, the density of the liquid, rho v square?
Uh, yeah, density of the fluid. We haven't
Uh,
mentioned anything about the fluid. So density of the fluid divided by U
v.
characteristic velocity divided by
U. Okay,
yeah infinity square.
okay, got it.
I'm saying U inlet. Now you can say U
Yes, sir,
infinity
got it.
also, but yeah.
Yes, sir. U.
Okay, so let us do this. See here, one thing is there that you have to choose a parameter which is representing a pressure in a pressure. Similarly, in temperature, the parameter should be representing the temperature. In case of coordinates, it should be parameter representing the coordinates. Velocity parameters representing the velocities. Okay. So let us do for a two-dimensional system, 2D Navier equation. So let continuity equation. Continuity equation is del u del x plus del u del y is equals to 0. So del u del y, how will do for del u del x? Del u del x can be written as, you can use a chain rule. Okay. So del u star del u star del x star del x star del x, like this. Okay, or you can directly substitute the values of del and del x. U value is u star u in, and x and x is equals to x star h. So u in and h, they are constants. So you take them out. So finally you left with del u star, del x star, right? Similarly, uh, del v del y is equals to, either you can write chain rule or v star u in divided by del y star h. You can get u in h del v star del y star. Now you add this, you substitute in this equation. So you get u in h del u star del x star plus u in h del v star del y star is equals to 0. So finally you can write in a non-dimensional form plus del v star del y star is equals to 0. This is a non-dimensional form of the continuity equation. Now let us move on to the momentum equation. X momentum equation goes like del u del t plus u del x plus v del u del y is equals to minus del p del x plus mu del 2u del x2 plus del 2u del y2. Okay. So first go for this del u del t. Del u del t can be written as del u star u infinite u inlet, and t will be tau into h divided by u in. So finally you will get it like u in square h del u star del tau. Okay. So this is one. Now u del u del x. U del u del x, this can be represented as u star u in and del u star u in del x star h. So u del u del x can be written as u in square by h u star del u star del x star. Similarly, we can write for v del u del x is equals to u in h v star del u star del y star. Okay. Now about del p del x. So that is nothing but del p bar. Your gravity is already incorporated in that. So this will be p star rho u in square divided by del x star h. So rho u in infinity, they are constant. They are constant. And they can be taken out. So similarly, this next term del 2u del x2 can be written as del x of del u del x. Okay, so del x del of del x star h del of del x star h u star u in. So you can get u in h square del 2 u star del x star 2. So similarly, for del 2u del y2, you can write like u in, because characteristics variables are same, so they will remain same. So del 2 u star del y star square. Okay. So substituting in this equation, we can write them like rho u in square h del u star del tau plus, so u in square h in the bracket u star del u star del x star plus v star del u star del y star, okay, minus is equals to minus del p del x. So del p del x is rho u in square divided by h del p star del x star, and this del u del 2u del x2 del 2u del y2, that can be written u in h square in the bracket. Here you have a mu del 2u star del x star 2 plus del 2u star del y star. So if you divide this, equation throughout by, or if you multiply this equation throughout by h, multiply above equation by h rho u in square, so you get del u del tau plus u star del u star del x star plus v star del v star del u star del u star del y star plus sorry, and then minus del p del p star del x star plus, now here you will get a term like 1 rho vd upon mu, like this. Del 2u star del x star 2 plus del 2u star del y star 2. Now this term is a known term to you. Okay. Here Reynolds number, if you remember, Reynolds number Re is equals to rho v, a characteristic dimension, divided by viscosity. So if you substitute in this equation, we get right hand side equals to del p star del x star plus 1 upon Re and the right hand side. Similarly, you can get a y equation. Similarly, the same equation can be followed for y. because our non-dimensional characteristic dimensions are same in y direction. We can write this for V star also in the same manner, plus U star del V star del X star plus V star del V star del Y star is equals to minus del P star del Y star plus 1 upon rho, means 1 upon Re. Del 2 V star del X star 2 plus del 2 V star del Y star 2. Okay. Okay. Now for temperature equation, now this is similarly we got this for y momentum equation. We got this. Okay. For temperature equation, for energy equation, our energy equation is rho Cp del T del T plus U del T del X plus V del T del Y is equals to K del 2T del X2 plus del 2T del Y2. Okay, so del T del tau we can del T del tau can be written like del. What is T? Now here T we have to we should get T. Okay, T star is equals to T minus Ts divided by T infinity minus Ts. From this, T will be equal to, from this T will be equal to T star T infinity minus Ts plus Ts. This. So you substitute this T here. So T is nothing but T star. This Ts, T infinity minus Ts plus Ts divided by tau, del tau. Tau is, you have to write T tau. T is T, this T, not tau. Here T is T. T is tau H divided by Un. So here this delta T infinity Ts, they are known quantities. Okay. So this is a constant. So you take it out from your this equation. So it comes like T infinity minus Ts will come out, and only del T star will remain. Del Ts will become 0. And here you have U in coming and U in divided by H. Del T del tau. U in T infinity minus Ts divided by H del T. So this is a first equation for that. Then del T del X is nothing but del T star T infinity minus Ts plus Ts divided by del X star H. So this is coming like, and you have U also. So U is nothing but U infinity U in. So you have U in divided by H, T infinity minus Ts, T infinity minus Ts divided by T U star del T star del X star. Similarly, V del T del Y will be equals to U in H T infinity minus Ts V star del T star del Y star. Okay. And del 2T del X2, this will be again del of del X of del T del X. Okay. And this you will get. Now you know how to get this. So I'll just simply write a final expression, which is a simple one. So T infinity minus Ts divided by H square del 2T star del X2 del X star 2. Similarly, del 2T del Y2 will be also T infinity minus Ts divided by H square del 2T star del Y star square. Substituting in the equation, you will get a final substitute. So after substituting, you will get an expression like rho Cp U in T infinity minus Ts divided by H del tau del T star divided by del tau plus rho Cp T infinity minus Ts U in H, and in the bracket U star del T star del X star plus V star del T star del Y star. This will be equals to K T infinity minus Ts divided by H square, and you have the other terms. Okay, now you divide these whole expression by rho Cp U in H, or you multiply by H divided by rho Cp in delta T. Okay, so I'll just write multiply above equation, multiply by H divided by rho Cp U in T infinity minus Ts. So multiplying by this, you will get a expression that del, excuse me. Now here you will come across with two separate terms. Okay. Now whenever you non-dimensionalize the thing, then after you see that, now here what I see is that I will get these variables here like K is already there, rho, Cp and U in and H. These variables will be present here. And del 2T, that now this here you see you have to combine these variables into some non-dimensional numbers. Some means those are connected to this. So one non-dimensional number, that is Re, Reynolds number, is defined as rho V and H characteristic dimension divided by mu. And there is another non-dimensional number which is called as Prandtl number, which was given by mu Cp by K. Okay. So you see here, these some combinations are there. So you can write this right hand side by like this: mu rho u in H and K mu Cp. Mu get cancelled, so you get finally K rho Cp u in H. But we got now in terms of a proper non-dimensional numbers, combination of variables. So we can write this as a function of REPR and right hand size. Okay. So everything we got in a non-dimensionalized form, and our non-dimensionalized Navier-Stokes equation now looks like del dot u star, okay, is equals to 0 in a coordinate free form. Del u star del tau plus u star dot del u star is equals to minus gradient of pressure, that is P star, plus 1 by Re del square u star, and temperature equation del T del tau plus u star dot T and 1 upon Re Prandtl number del square T. You see? So now this is a final form. So what is the physical significance? Now look at the physical significance of this. Now everything is varying from 0 to 1. What is physical? So what is Reynolds number? Reynolds number is nothing but rho Vd upon mu. So what is rho V u in rho Vd upon mu? This is nothing but is equals to called as inertia force, because inertia force divided by viscous force. Okay. So what it represent? Rho u h. Rho u h represents this part. This is a inertia part. This is a inertia part. And this is a, I mean, this right hand side is a viscous part. This particular is a viscous part. Okay. So Reynolds number actually represent the ratio between these two terms, left first term and right term, if this pressure gradient is negligible. If this pressure gradient is negligible, then if Re is very high, if Re is very high, Re is high, what does it mean? Re is high means mu should be small, isn't it? Mu should be small means it is not a viscous, highly viscous fluid. Okay. So it means that Re high means rho u h should be high. It means u infinity should be high. And if the velocity is high, means this inertia term, which is velocity dominant, uh, it is a non-linear term. So u to the power is 2. So the dominance of the inertia will be more. Okay. So dominant of the inertia will be more. So if this is Re is very high, then then dominant of the inertia will be, okay. Then what about Prandtl number? Prandtl number is momentum diffusion divided by viscous diffusion. Sorry, thermal diffusion. It is connecting the momentum equation with the okay. So momentum diffusion divided by the thermal diffusion. What is diffusion? This viscous diffusion is nothing but momentum diffusion. Okay, and this is a thermal diffusion. This is a inertia term. This is a these are convection terms, convection, and this is a diffusion term. This is a thermal diffusion. Okay. The combination of Reynolds number and Prandtl number is called as Peclet number. Peclet number. This is nothing but Peclet is equals to if you write for REPR, combination of REPR, then you will get U H UN divided by H alpha. So here one important thing is, say we are talking about air or say we are talking about water. Now once we say that RE number is same, RE number is say 100, RE number is 100. So it doesn't matter whether I'm talking about the fluid, isn't it? It doesn't matter whether I'm talking about a particular fluid or not. So results in Reynolds or non-dimensional parameters are independent of the fluid. I can always write this RE 100 by combining this rho, U and H and mu such a way that I get always 100. So I can adjust these parameters rho, mu, U and H is fixed. So U also may be fixed given. So or you can vary and you can adjust these so you can make the Reynolds number constant. So suppose if the Reynolds number is constant, but the Prandtl number for the air the Prandtl number is around 0.7, and for water the Prandtl number is high, that is around 10, 6 to 10. Okay. Now you see the difference between the Prandtl number and this. So REPR in case of air will be REPR will be, that is nothing but Peclet number will be a small, and for water this Peclet number will be large. So what does it mean? If Peclet number is small, what does it mean? If Peclet number is small means U in is small, alpha is large. So inertia is not that dominant. Inertia is inertia is insignificant compared to alpha. If alpha is if P is large means U in is large. Okay. So based on the Reynolds number, you can see the effect of which terms need to be considered and which terms need not to be considered. Okay. At higher RE, these your inertia forces are very significant. So these inertia forces will play a major role at high RE. RE is high. And since they are non-linear terms, they tend to give you a problem of turbulence. They try to make the flow turbulent, unpredictable, chaotic. However, the effect of this momentum term is to diffuse. Okay. So diffuse these velocities, like it is suppressing, but it is adding. And in case of this here, if you are looking at now, this is we can also say this is a Peclet number, 1 by Peclet. So if Peclet number is very small, then we can we know that u this effect is very small. Diffusion effect is more dominant. And if the Peclet number is large, it means that these terms, convection terms, are more dominating compared to the diffusion terms. So sometimes you can neglect some of the terms based on the non-dimensional parameters also. You can simplify the equations. Okay. Another advantage of this non-dimensional equation is that from these equations, we can simplify, we can simplify the governing equations, okay, based on the values of dominance of non-dimensional numbers. Okay. So for this particular combination of non-dimensional variables, we got for this particular combination u star u divided by u in, we and like that we got these non-dimensional parameters. But some other some other this definitions of these non-dimensional numbers, you can get some other terms. Like here you may get the gravity pressure effects. Okay, so you may get Prandtl number as also a non-dimensional number in this equation somewhere. Okay, if you have a buoyancy term, then you may get a Richardson number and like this. So it depends upon the definition of the and that is a very crucial step, crucial, critical, and as well as I said, it is a sort of trial and error. Okay, there is no particular okay. Now in this case, as I said, the air and water. So suppose you want to draw the temperature profiles. Suppose T temperature profiles you want to draw as a function of H. Now, in case of air, your temperature profile will look like this. Your temperature profile will look like this. Okay. However, in case of at the same location, the temperature profile of the water will be like this. So this is for water and this is for air. So what do you see? Why this temperature is high in case of water and temperature has reached a less small value as compared to the other one? That depends upon what is the reason you will mention. What is the reason you will mention? Prandtl number, right? What is the Prandtl number of air? Air is small. Prandtl number of water is high. Prandtl number is nothing but equals to momentum diffusion divided by thermal diffusion. So mu Cp by K, mu Cp by K. So mu Cp by K. So it represents mu and K. So when P Prandtl number is small, means K is high, means mu is small. Okay, viscosity is small, K is high. So you see in case of water, your water Prandtl number is high, means K is small, mu is high. So there are less resistance. There is less resistance for flow to flow. So in a certain time, the flow here uh, will be, because of highly viscous nature, it will have a large resistance. So flow will flow this much distance. However, in other case, the flow will be moving, for faster. Since flow is moving faster, the transfer of energy is taking at large distance. And the quicker actions are happening because of these convective effects are also coming into picture. Okay, so this kind of justifications you should be able to predict from these non-dimensional numbers. Okay, based on the talking, if you are talking about certain fluids and like. Okay, so in nutshell, I can write here that this U dot del T, if this is a small, which means that convective heat transfer due to U is negligible. And del square T is large if A is small. U is small. And this can be small, and then I can say that conduction heat transfer dominates. Okay. So Peclet number talks about convection dominance or conduction dominance. Okay. Okay, I'll just take a 1 minute to take one problem, not exactly connected, but just consider a non-dimensional velocity profile. U star is equals to Y star divided by delta, where non-dimensional boundary layer thickness delta is equals to C x star to the power half, and C is constant. Okay, as shown in figure. So the figure goes like this. As one student was asking, that flow or a flat plate, it is a flat plate. It is having this distance x star and things are varying in y star direction. So y is becoming a characteristic dimension, and here you have a boundary layer. So this is a delta of that boundary layer, which is a function of x star. C is a constant, and the velocity is given. The velocities are like this. So here at the end, it is like u star. This is a u star velocity. This is a non-dimensional profile is given. Now with this, it is asked determine the v star. What is the v star inside? Determine v star. Determine v star. Okay. So how do you v star in a BL? In BL boundary layer. How do you find this? Suppose I have been given a u star and I have been asked v star. How will do that? Any idea?
Dou u star by dou x star will be
Huh?
equated to
Viknesh?
sir, dou u star by dou x star is there, no sir?
Huh.
That equation.
Huh.
There with that we analytic
Yeah.
function.
So yeah. So first thing first is we should look for laws. Okay. First thing is you should look for laws. Which law can govern this? So we know that continuity equation, momentum, and energy equation. So is energy is there? No. Momentum is there, but how you can get from momentum equation? Because pressure is there. Pressure is not given in this problem, isn't it? So other equation left is you have this del u star, del x star plus del v star, del y star, isn't it? Now from this equation, you can substitute for u star, and so u star and this x star, and you can get this. So del u del x star, this will become like y star c x star half plus already del v star del y star is equals to 0. So this will give you y star divided by twice c x star 3 by 2 plus del v star del y star is equals to 0. So essentially del v star, del v star del y star is equals to y star 2 c x 3 by 2. This is star. Now integrating this, you can get v star. So v star will be equals to y star square divided by 4 c x star 3 by 2. This is what you got. Now I'm just making it in a simplified form, which will be like y star c x star and y star 4x star. So that we know that this one is already a u star. We are writing v star in terms of u star and y star 4x star. Okay. So any answer is correct. This answer is correct. This also, and so this also.
Sir,
Now
should we consider the constant of integration, sir, and apply boundary conditions?
yeah, so that constant of integration, now boundary conditions are not given. So you assume that it is 0.
Okay.
Okay. So y is equals to 0, v is equals to 0. Okay, so that condition you can use and we can get that boundary condition. If it is not given also, you can, from the physics that y star is equals to 0, v star is equals to 0. That is a boundary condition. At other, we do not know v star, what is the value of v star. So you can use that and you will get this. Okay, now my interest is to show you how v star varies with u star. Okay, so v star u star will be equals to y star divided by 4x star. So if you plot this variation, it will vary like this: v star u star as a function of x star. It will vary like this. What does it mean? V star u star is getting small, means u star is increasing and v star is decreasing, isn't it? At this point, you see, v star is decreasing and u star is increasing. So this is a conservation principle, just to show you the meaning of conservation. So here, more in this, suppose in this domain, more v is more and u is small. U is small. Okay, so dominance is in x direction. V star is very negligible, becoming negligible once it becomes fully developed, kind of fully developed boundary layer. Okay, so you should be able to do some manipulations like this. You should be in a position to do the non-dimensionalization and recall all the non-dimensional parameters you know in your past and their definitions, such a way that you should be able to understand the physical significance of these governing equations. Or if it is asked to simplify, as I said, we can simplify the governing equations. You should be able to simplify on those bases. Okay, so we'll see in the next class. Thank you.